today's video we will discuss about application of Biot-Savart's law. So in last video I told you about Biot-Savart's law. You got the formula of Biot-Savart's law. Now say there is a ring or circular coil like this carrying current. The current is going like this, okay, and then it is coming this way. Now see, this ring, you have to understand this concept in a three-dimensional way. This ring is not on the plane of this paper, but it is in YZ plane. This is y-axis, x-axis, z-axis is outward to the plane of the paper, and YZ plane means this is the plane, this plane. Okay, it is, I think you have understood this one. So the ring is on this plane. That means, okay, just an example, suppose this is a cylinder, okay, this is a cylinder. Now you have understood the cylinder, since it is a three-dimensional object. Okay, now from this cylinder, if you cut this part, how it will be, or in which plane it will be? It will be in a plane perpendicular to the plane of the paper, right? Perpendicular. So the same way the ring is placed, perpendicular to the plane of the paper, because the paper plane is the xy plane, x-axis, y-axis, both the axes are on the plane of the paper, but the ring is not on this plane. This is in YZ plane, perpendicular. Okay, right? Like if you hold one book on this plane of paper like this, okay, then the ring will be on that plane. So I hope you have understood. Okay, YZ plane. Anyways, now what happened is, on this ring we considered a small elemental length, very small length, dl. Actually here what we are finding is, we have considered a point P. At this point we have to find out the magnetic field produced on the axis of the circular loop, because the point P is on the axis. This is the circular loop, this is the axis of the circular loop, and point P is on the axis. So we have to find out the total magnetic field at this point P. And why the magnetic field will be produced? Because of the current flowing through the circular coil. Okay, now what we have done is, we have considered a small elemental length dl, which is at a distance of small r from the experimental point P. The radius of the circular loop is capital R. So if this is capital R, and if the point P is at a distance of x from the center, this one, then this is like a triangle. The hypotenuse will be root over r square plus x square by Pythagoras theorem. So that hypotenuse is small r also. That is the distance of P from dl. Now first of all we will find out that this dl length, how much magnetic field it is creating here, and then we will find out the total magnetic field produced by the whole conductor or the whole circular ring. So the concept is like, first we will find the magnetic field for dl, then we will integrate it for the whole circular ring. Alright, so here certain things I have written, you can read this part, but I am explaining. Suppose this dl length, it is producing a magnetic field of dB at point P. The main thing is the diagram. You have to know this diagram, and you have to be able to explain the diagram. So this is P point, and if you see here, the magnetic field is dB produced by dl length. Why dl length is producing the magnetic field? Because current is flowing through this current like this. Okay, now see why the magnetic field is like this side. If you remember Biot-Savart's law, what was that? Mu naught by 4 pi vector form. Okay, I dl cross r unit vector, or below it was r cube. It was something like this. Okay, right? Then here you see this theta, I mean this one, no, and this side what we have, dB, in left hand side. So this part is a scalar one. This one. The direction of dB depends on this dl cross r, cross product. So we know that dB should be in a plane perpendicular to the plane containing dl and r. The plane where dl and r is lying, dB will be perpendicular to this plane. Now in which plane dl and r is lying? R is this one, little bent, this one. Where is dl? dl is this part. Now see, this dl is not on the plane of the paper, right? As I already told you that the circle itself is not on the plane, it is in yz plane. So dl is also something like this. This is dl actually. Okay. So if this is dl, if this is r, in which plane they are containing? The plane is, okay, just a second. This is the plane where dl and r is lying. So dB should be perpendicular to the plane, that is why dB is like this, it's oblique, like this, perpendicular to this plane where dl and r is lying. Okay, that is why the direction of dB is perpendicular to dl and r, this one. Now this dB, okay, another thing, see what is the angle between dl and r. dl, I told you dl is actually not on the plane of the paper, but it is something like this. R is this one, so this angle is actually 90 degree. Alright, remember this concept, dl and r is 90 degree angle it is making. Another angle is there, theta. This is the angle between r and the radius of the ring. Okay, fine. So now see this dB. dB is resolved into two components because it is a vector, dB sin theta and dB cos theta. This side is cos theta, this side is sin theta. And since this angle is theta, then this angle will also be theta, by the principle that angle between two lines is equal to the angle between their perpendiculars. You got this concept many times. Okay, so this is theta. Now for this dl length we got dB, we resolved it into two parts, sin theta cos theta component. In the same way, here if you consider another dl length, in which direction it will create the magnetic field, you just take the mirror image of the diagram, how it should be. Then if this is the part for which you want to calculate the magnetic field at P, then this will be the direction of dB, just like the upper part. Take the mirror image or imagine the mirror image. Okay, if it is so, if you have another dB here, again we will resolve it into two parts. D sin theta will be downward, dB sin theta will be downward, dB cos theta this side. So this sin theta and this sin theta are opposite and equal, so they must cancel each other. So if they cancel each other, which component will be in existence? Only dB cos theta. For this part also dB cos theta, this part also dB cos theta. For other parts also we have only one component in existence, that is dB cos theta. Okay, so if this is dB cos theta, that means dl length at point P is actually producing dB cos theta magnetic field. So the whole ring will produce how much magnetic field? Integration of dB cos theta. So that is why the total magnetic field produced at point P is this value. Integration, closed integration, closed means we are taking the closed circular path, I mean the closed circle we are taking. Okay, so that is why closed integration of what? dB cos theta. B is the total magnetic field. Then we will find out, we will calculate the rest part. Okay, so see here, dB from Ampere's circuital law, what was the expression? Not the vector, okay, vector form, alright, vector form also you can think. What was that? Mu naught I by mu naught by 4, this one, no? Mu naught by 4 pi, then I dl Okay, I am writing the general one. Okay, ideal sine theta by r square. What is this theta? Angle between dl and r. And just now I told you that dl is like this, r is this one, so angle is 90 degree. So sine theta is 90 actually. Remember that this theta and this theta are not same. Huh? This theta is the angle between dl and r. This one. So anyways, this theta is 90, sine 90 is 1. So this part will vanish. What will have? IDL. This is dl. IDL by r square. Mu naught by 4 pi IDL by r square. This one. For dB. For cos theta, if this is the triangle, cos theta means it is base by hypotenuse. Which one is base? R. Hypotenuse is this one. Means smaller, no? So capital R by small r. Next, r square and r becomes r cube. Then this one. Next step. See, in this whole equation, only dl is the variable because dl is changing and it will cover the whole circumference of the circle. Rest things are constant. So actually, we can take the rest term outside. One thing we have done here, r cube can be written as like this, no? Isn't it? Because r is this value. This value means r is actually r square plus x square. If you don't write the square root, we can write the power as half. And along with that, again we have cube also. So what is the total power? Half into 3 means 3 by 2. So this is r actually, r cube, right? So in place of r cube, we can write this value, r square plus x square 3 by 2. Then as I told you that inside integration we have only dl. Okay, so if you integrate this dl, it will cover up the whole circumference, so it will be 2 pi r. Okay, so here it is done. dl is taken under integration, 2 pi r. Then certain things will get cancelled like pi, 2, 2 and 4, and finally we get this equation. Okay, so this is the equation of magnetic field at point P, which is on the axis of a circular coil carrying current. And this is the application of Biot-Savart's law because we are using the formula from Biot-Savart's law. Another thing I have written here, for n turns, that means here only one turn of the ring is present. If there are many turns, like n number of turns are there, then the total magnetic field will be multiplied by n. Okay, rest thing will remain same. So we can write it like this. Then special cases. Case number 1, if the point P means this point, if it is far away from the circular ring, then certainly the value of x will be very greater than the radius, or in other words, radius will be very smaller than x. If it is so, r can be neglected. Under this condition, this capital R is very small, so in the denominator here small r, capital R can be neglected. If we do so, here we can write 0, so it will be 2x square. This 2 and this square will get cancelled, it will be x cube. So mu naught I r square by 2x cube, this one. Okay, next another condition, if the magnetic field is at the center of the coil, that means the point P is at the nothing but the center of the coil. If it is so, then x will be 0, no? If you are bringing this point P closer and to the center, x will become 0. The distance, there is no distance actually, right? So if x is 0, what will happen to this equation? Substitute x as 0, square of r and this 2 will get cancelled, this will be r cube, and above we have r square, so r square r cube will get cancelled, below we have only r. So the equation becomes mu naught I by 2r. Okay. So I hope this part is clear. Then next is Ampere's circuital law. It also has some application, but today I will just tell you the statement and the proof of it. statement is that it states that the line integral of the magnetic field around any closed path in a free space is equal to absolute permeability times the net current passing through any surface enclosed by the closed path. Okay. The meaning is that suppose there is a conductor carrying current like this, and we know that around the conductor there will be magnetic field. How we can get that? By the right hand thumb rule. Current this side, then the curl of all the four fingers, it is something like this, circular, huh? This is magnetic field, this one. So that's what I have drawn here. Okay, so according to this law, the line integral, this is called line integral, means like in Gauss's law, E dot ds, this is called surface integral because it was surface, no? ds. Here it is dl, l means length, so we call it line integral. So this line integral of magnetic field means this magnetic field is here, no? B. Line integral of this field means it is closed integration B dot dl. This is called line integration of magnetic field, which is equal to mu naught times, means absolute permeability times of the net current which is producing the magnetic field, or the net current enclosed by the closed path. How much is the current enclosed? I is the current which is flowing through the straight conductor, and as a result around the conductor there is a formation of magnetic field B. Line integral of this magnetic field gives us mu naught times of the current enclosed by it. Okay. To prove it, we start with left hand side. So we wrote this one. So from this B dot dl, see here, okay, just a second. Okay. Here we consider a small length dl, and remember that the direction of dl, since we are moving in this way, direction of dl is this side. Okay, and the direction of B is also this side, isn't it? By the curl of our four fingers we got this one, that the direction of B is like this here at this particular region. Again here the direction of B is this side, no? Anyways, so here B and DL are in the same direction, so angle between them is 0 degree. Since it is dot, it should be B dl cos of theta. So theta 0 means cos theta will be 1, so it is B dl. B comes outside the integration, inside integration we have dl. Now B means it is the magnetic field produced by a straight conductor having infinite length, because the length of the conductor is nowhere specified. So for infinite conductor, the expression for magnetic field is this one. This value you remember, okay? Mu naught I by 2 pi r. This one is for infinite straight conductor, which value and this value we are substituting here in place of B. DL will be, DL is a small length. If you integrate it through the whole part, then that should cover up the whole circumference, which is 2 pi r. Capital R is the is the radius of this part. This is the center of the circle, so this is the radius. Okay, so 2 pi r. Now from this, see 2 pi r get cancelled. What we got? Mu naught I, which is the right hand side of this law. Okay, so this is a way how we can prove Ampere. We can prove Ampere circuital law, and next day we will discuss the application of Ampere circuital law. Thank you.